It looks beautiful, shiny and golden. So safe, so harmless. But it's not. Believe me, this is beauty and the beast on steroids. This is one of the most bloody lethal solutions you're ever going to get. It's also interesting in that it appears on the cover of Science this week, a fairly high-profile science publication, along with an article on this, which, to be fair, has an entire army of authors, and you'll be maybe interested to know it actually contains an acknowledgement to this channel. Because thanks to your support, either through watching this channel or supporting it through Patreon, I basically now have a fully equipped research lab that actually made real contributions to this research. So why were we looking at this evil gold solution in the first place? And what could possibly make it so interesting that it would end up on the cover of Science magazine? That is a fascinating question with an even more fascinating answer. Allow me to explain. Now I'm going to start here with two very civilian-looking liquids, very common liquids in the universe. One of them is liquid water, and it makes up about 70% of your body. The other is liquid ammonia, which is horrific stuff. Well, at least for us water-based life forms. Now, it turns out in the wide world, ammonia is one of those liquids that's actually being pitched as an alternative solvent for alien life. You know, just like we have water in our bodies, maybe there is alien life with ammonia in their bodies. And if I show you what these things look like in a molecular dynamics simulation, it's just a computer generation of what's happening at an atomistic level. But it turns out, structurally, it's about right. So you see the H2O water molecules and the NH3 ammonia molecules. And you can see that they look kind of samey. And both of these molecules share another property, that in the liquid, they are very strongly hydrogen bonded together. You see, the way it goes is usually the heavier the molecular weight of a molecule, the higher its boiling point. But both water and ammonia are peculiar in their very small molecules that have very high relative boiling points. And this is because the molecules are held together really strongly by these things called hydrogen bonds. And maybe just to throw this into harsh relief, I'm going to add some air to my droplet of water here. And that's about right for the density of the molecules in air, both nitrogen and oxygen, and the density in liquid water. And if you're interested in this sort of thing, I did another video just almost entirely on this called Life in the Bulkhead. So what you see is when the air molecules hit the surface, they stick to the surface, but only very weakly by an interaction called van der Waals interactions. And those are very weak, so quite often the molecules will just be kicked off the water's surface. However, the water molecules are held together by these very strong interactions between these very polar water molecules called hydrogen bonds. And they are absolutely critical for life, which is one of the reasons why ammonia has also been pitched as a solvent for life. Now, for those who have followed this channel for a while, you'll know that I have this thing where I every now and again debunk a free water from air device and why they're so bad. And the reason is basically because when you get gaseous water and you condense it, you form a load of these hydrogen bonds. And if you don't take the energy out of the solution, then all the molecules just fly apart again. And it's taking out that huge amount of energy from forming all the hydrogen bonds, which makes dehumidifiers so expensive. And the flip side is true, that if you want to break all those hydrogen bonds and say, for instance, boil the water, that takes a colossal amount of energy from the environment. Now, the same general properties apply to ammonia, which is again a very strongly hydrogen bonded liquid, which is why liquid ammonia at a mere minus 30 degrees Celsius will give you far more severe burns than liquid nitrogen at minus 200 degrees Celsius. And that shouldn't be like that. That's a leaky joint. That's liquid nitrogen coming out of there. And this isn't something I just read in a book. And this one's kind of first-hand experience. But why is that? Why can the liquid that is far warmer burn you much more nastily? And it's a couple of factors. When you put your finger in liquid nitrogen, it tends to form a gas layer around your finger, which limits the rate at which the liquid nitrogen can take the heat out of your finger. Whereas ammonia will stick to your finger, just like a drop of water would. And when liquid nitrogen boils, it's like Like I was saying, the forces that hold the nitrogen molecules together are very weak, so boiling the nitrogen doesn't take much energy, whereas boiling the liquid ammonia, getting it to evaporate, means you've got to break all of those hydrogen bonds, and that sucks out a huge amount of energy. In practice, this is why it takes 5 times more energy to boil liquid ammonia than liquid nitrogen. And it's not just thermodynamically evil, this ammonia stuff. A good sniff of ammonia gas is like being punched in the face. It's a gas, so as you get this going, you'll be able to hear the gas going. Oh, yeah, even now, you get a good whiff of ammonia, and it's kind of like getting hit in the face. It's, yeah, that's how sharp it is. It's really sharp, but relatively short-lived. And then it's more or less the same if it gets in your eyes. It stings like crazy, but it doesn't have a long period of time. And in terms of toxicity, it's not actually that bad. 30 seconds after a sniff of ammonia, and you're basically 100% recovered. But damn, do you know if there is a leak of this stuff? Now, I should stress there's a difference between the ammonia you get under the sink. That's basically a solution that's mostly water, about 90% water and 10% ammonia. And here what I have is pure water and pure liquid ammonia. Now, water and ammonia share some other interesting properties too, most notably their fascinating reaction with the alkali metals. The alkali metals are, of course, famous for exploding when they're thrown into water.
Oh, jeez. Catches on fire and then it explodes.
Yeah!
There it is. That's nice.
Don't yell.
Yeah, kid, be responsible. Don't yell while we're blowing up the lake. But when you sit down and think about it, that shouldn't happen. The metal is on one side and the water is on the other, and when they react, they generate heat, sodium hydroxide, which tends to keep the reagent separate, and hydrogen gas, which also tends to keep the alkali metal and the water separate. So the reaction should be self-limiting, but it's not. It explodes. And it explodes in less than a millisecond. So why does that happen? Well, the answer comes with what happens the instant the metal comes into contact with the water, which is the electrons fall off the metal and into the water. The electrons are actually happier in the water, where they can form these little cavities of these polar water molecules, than they are in the metal. And seeing as you've now got these slightly separated electrons and positively charged metal ions, once the lateral repulsion there becomes equal to the surface tension, it goes boom. Now this work was kind of noteworthy in that it got published in Nature Chemistry, and it acknowledged the support of this channel because the project genuinely started on this channel and was supported by this channel. Now, I was saying that water and ammonia and their reaction with alkali metals are both very interesting. And so, when you add the alkali metals to ammonia, the electrons fall off, but they don't actually react with the ammonia. They just stay there in these stable little cavities. And the reason you get those stable little cavities is the same reason that you get all the hydrogen bonds. It's the strong polarity of the bonds. It's just that in ammonia, the electrons in those cavities can be stable for weeks. And it turns out that those electrons also have an associated color, which is blue. And this means you can do some crazy experiments. Like if you just get your liquid ammonia and dissolve a little bit of salt in it, like salt dissolves in water, then you pass electricity through it. And at the cathode, the electrons just fall off into solution to give solvated electrons. That's actually the electrons falling off the wire that you're looking at there. But that's not really even the most interesting thing here. When you increase the concentration, it goes from blue through a sort of purpley color to metallic gold, which is fascinating if you think about it. So here I already have the gold solution and I'm condensing some ammonia on top of it. And when those pure drops of ammonia hit the surface of the gold solution, they dilute it somewhat and it turns blue. And then as the concentration in those little droplets increases, it goes back to gold again. Yeah, this is just so weird on so many levels. You're taking a liquid that is very much like water, and it's not reacting with the metal, it's actually dissolving it. And at first it just behaves kind of like an electrolyte, and as the concentration gets really high, it gets the properties of a metal. And once you get up to that gold solution, it's got better conductivity than the metal you dissolved in there in the first place. So you can take something like sodium, which is a reasonable conductor of electricity, and you dissolve in all this water-like molecule into it, and it actually becomes a better conductor of electricity. Now, I really can't stress how weird these things are. You look out on the window onto the wide world. What you see is made up of atoms. Those atoms are nuclei, which form sort of potential wells in which electrons sit. The electrons in this blue solution, well, they're kind of like potential wells formed by this strongly hydrogen-bonded liquid, but there's no nucleus in the middle of them. They're just free electrons sat in these cavities in solution. So how does a solution of electrons become a metal? Well, you recall I was saying these electrons are in potential wells. And if all this talk about potential wells sounds a little too much like Star Trek talk or something, it's not. Just let me show you how simple this actually is. You see, one potential well is much the same as another. Now, these potential wells are electrostatic in nature, but if you put them in the form of another sort of potential well, a gravitational potential well, it suddenly becomes ridiculously easy to grasp what's going on with this research level X-ray particle physics. So, for instance, if I put a kilogram weight into a sink, it takes less energy to get it out of that potential well than it would to get it out of, say, for instance, a bathtub or a well. This is exactly the same thing, it's just on an atomistic scale. These are the potential wells of the universe. The electrons in the potential wells formed by nuclei are very deep and very well formed, and it takes a lot of energy to get the electrons out of those, which is a good thing, and why all the atoms that you see around you are fairly stable. However, the potential well of these solvated electrons, they're a much shallower well, and they're much more floppy and poorly defined. And that's the bit that we're really interested in. We want to map out this transition between solvated electrons and metals. Now, fortunately, there is a technique that allows you to do this sort of thing. It's called photoelectron spectroscopy. The concept's actually pretty simple. Give the electrons in those holes a fixed-sized whack, and the electrons shoot off, and the energy that they shoot off with is the energy that you put into the kick in the first place, minus the energy it took to get out of the hole. And that fixed energy whack comes in the form of monochromatic X-rays. So you know how much energy you put in, you measure the speed that the electrons come off at, and therefore what is left must be the depth of the potential well that the electron came out of. So this gives you an energy landscape of the material that you're looking at. There's just one or two tiny technical problems. The prime one being, this technique is almost impossible for studying these solvated electrons in solution. You see, photoelectron spectroscopy requires almost a complete vacuum. In fact, photoelectron spectroscopy was thought to be impossible for a long time on volatile liquids because if you put liquids into a vacuum, they evaporate and it's not a vacuum anymore. Then someone who was clearly a fairly smart guy came up with the idea of using liquid microjets. You squirt your liquid into a vacuum chamber in a very fine jet, and then you hit that very fine jet, which is about the size of a human hair, with an X-ray beam, which is also about the size of a human hair, and that ejects electrons that then have to go through a hole about the size of a human hair to a very high vacuum chamber where the energy of those electrons can be measured. And believe it or not, this technique actually works. Cool, so all we now have to do is work out how to do that with evil water and evil water that bursts into flames when it's sprayed into air. Nonetheless, we managed to get stable microjets of these solutions and zap them with X-rays and record the energy of the outcoming photoelectrons. Now, so what you got here is a whole host of concentrations going from the blue solutions up to the finest gold. So the higher the number there at the bottom, that's the deeper the hole that the electron was kicked out from. Now, what makes this super cute is you see where it rises up there at about 8 electron volts. That's actually the energy of kicking out the electrons from the superstable nitrogen atoms in the ammonia. And the peak at 2 electron volts, that's the solvated electron. And just so you know, photons of visible light are about 2 to 3 electron volts in energy. Now, that's not quite what's being measured here, but we're measuring the depth of the holes that the electrons are coming out from in electron volts. But this does tell us that regular visible light would contain enough energy to kick some of these electrons out of the solution. But what about the transition? So what we found was at lower concentrations, you're knocking the electrons out of these little cavities. Cavities whose properties I would like to stress are happily concordant with quantum mechanical calculations that we also performed on these systems. And then as the concentration increases, you start seeing a band structure, complete with a Fermi edge. It starts to look more like a metal. You start seeing plasmons. What are plasmons? Well, it's kind of what you're looking at in a mirror. Those are plasmons. In more sciencey terms, they're more like resonant mean free path of electrons in a metal. But you can see them via photoelectron spectroscopy. And maybe to drive the point home, we actually did the photoelectron spectrum of sodium-potassium alloy as well, which by fortunate circumstance is actually a liquid at room temperature. And here is actually some footage of a microjet of sodium-potassium alloy. Now, another thing is just how stunningly internationalist work was, where it's got authors acknowledge the Helmholtz Center in Berlin, which is the Bessie synchrotron, that's where the measurements were made, the supercomputers at Ostrava, European Regional Development Funds, Charles University, the US National Science Foundation, State of Jersey, which I can tell you isn't a typo. That's not New Jersey, that's the original Jersey, as in the Channel Island Jersey. We got the Egyptian Ministry of Higher Education, and of course some renegade thanking his YouTube channel. But for me, maybe one of the most interesting things about all of this is some of the researchers here were actually from the Fritz Haber Institute. That's the same Fritz Haber who invented the Haber process, which is essentially a cost-effective way of making ammonia. And it turns out that that ammonia is absolutely critical for mankind. That ammonia produces the fertilizer that feeds about 1 person in 3 on the planet. And I gotta admit, there's part of me that's tempted to make just a video on how we made these jets, because it's actually quite interesting. You know, from the first very amateurish attempts, where we really didn't have a good idea of what we were doing. Don't get too picky here.
Yeah.
It's running.
Yeah.
Look at that! But you want to take a picture of my picture?
I'm taking a picture of your picture, yeah. Exactly what I'm doing.
I'll take a picture of the picture.
This is a kind of a...
Good. So,
From this
conceivably possible. Yeah, conceivably possible. That's how confident we were at the beginning. But eventually we did manage to get these rock-steady jets that would actually work in a vacuum. That, because...
It's not a screenshot.
Not a screenshot, but it's just beautiful. Although even at that, there were some surprises. But they're really sharp dendritic crystals, yeah?
Alt F4.
Oh, look at that. So in quick summary, we measured the photoelectron spectrum of solvated electrons in liquid ammonia from these blue electrolyte solutions through the metal transition all the way up to these metallic gold solutions. And in order to do this, we had to get a microjet of this very air-sensitive, cryogenic type liquid about the thickness of a human hair, then zap it with an intense X-ray beam, also about the thickness of a human hair, in this case from a powerful synchrotron, the Bessie synchrotron in Berlin. Then get the electrons blasted off that to go through a hole about the thickness of a human hair, and then measure the energy of those electrons within a fraction of an electron volt. That's it, it's the gold jet. That's beautiful.
I don't know if you'll get much better on that, right?
Okay guys, victory faces. Yeah! Victory faces, yes! Victory face. There we go.